So I just want to like showcase some stuff that I did. First, compilers. Yeah. So we're going to start with some very basic stuff. So let's just move my directories. I'll be like compilers. That's so first thing that I did is a shell. So I'll be like, okay, let's just show this. Cool. And there you go. That's our shell. So I don't know, I'm going to just type some commands. So first let's just start with a very simple thing. Let's say print 1. So control J executes, prints 1 as you would expect. Let's do something weird. Let's say we apply a header mark gate to the 0th qubit. So yeah, apparently there are like, no, not apparently, explicitly there are 5 qubits labeled from 0 to 4 inclusive. So let's apply header mark gate at 0. Let's apply it at, I don't know, let's just apply it at 0, not caring much. And then we'll do this. Okay, that's a parse error because that's not how you apply a quantum gate. So you apply it like this, right? And now let's just draw this, or let's just measure it. So I'll be like measure 0 into some variable. So first we need a variable. So we'll set let x whatever, we're just defining it. It's a variable. And now we'll say measure this. So measure 0 into x with, I don't know, let's say 100 repetitions, right? And so this will just basically like so this will internally like talk with Qiskit, right? So Qiskit is like this library, Python library that you have to actually like push push like HTTP protocols to the Qiskit like server, and there things get executed and then you get it back. So there are like real quantum computers there, and then you can execute it on that, and you can do it here as well. Just have to change like 1 or 2 lines of code in my code base, but just for the sake of like clarity, I'm running this on a virtual machine. All right, the virtual machine that Qiskit provides us, I'm running it on that. So yeah, but you could definitely run this on some actual hardware, right? So quantum computing is very much real in my language. All you have to do is just like change a few lines of code. That's it. But yeah, so for now we're just going to run this on a virtual machine. So it's like measure 0 into x and let's say 100 repetitions, and let's say I execute this thing. So now in x I have a dictionary. So if I say print x, it will, okay, control K is not anything, control J. So this will print me the number of times that you got the quantum state 0 versus when you got the quantum state 1. And this is like really useful because now, okay, so the first thing is if you are actually going to run this on a true, so like a quantum random number generator algorithm, like you can run this on a real quantum computer. In that case you can get you can get some really nice results. Like you can have very close to uniform distributions, right? So you just have to prepare quantum states which have equal distributions, and then you can get very uniform to that. So yeah, that's like a nice thing. You don't have to rely on the pseudo random number generators which use your time, which is like stored somewhere in your secondary memory and all that bullshit. Like none of that has to happen. You can straight up just apply a header market and then measure. So this is a very cheap way of using so okay, this is a very bad way of using quantum computing. There are much better things that you can do. For one, you can use Shor's algorithm, which is, okay, that's not up to the mark yet, but you can use algorithms like that. You can use a quantum support vector classifier or like anything basically. So okay, yeah, by the way, quantum support vector classifiers are real things now. Like they are in use. You can actually use them, and Qiskit even gives you proper code to use it. But we're not going to do that over here. This isn't like an intro to quantum thing. It's just like, it's not a quantum computing thing that I'm doing. It's just like an extension of MIPS that I've built, right, which I'm running everything on. Okay, this is actually just run Python. So if you want to use it like that, use it like that. I don't really care. But anyway, just to showcase my language, nothing complicated. Now let's draw what quantum circuit we actually have. So like draw Q, control J. Okay, that's incorrect, because what you have to do is run run draw Q. So draw Q is a function or a system call. Okay, that's bizarre. I guess it's draw QC, quantum circuit. Okay, whatever that was. Yeah, I'll just run it again. Draw quantum circuit. Yeah, so this is our quantum circuit. Yeah, so you have one classical bit and then a bunch of quantum bits, and so the 0th one you're applying a Hadamard gate to it, and then the whole state you're just measuring the 0th bit and you're storing in a classical bit, and then you're sending the results. Whatever, not a big deal. So this is just to showcase stuff. Okay, next thing, arrays. Yeah, so NumPy arrays. So what can we do? Good question. Let's do it like this. Okay, so I'll just say let x, or let capital X, since I want some other variable. That's going to be a vector. Yeah, and let me give it a shape. So I'll give it the shape 1, right? Just 1. Okay, 1 is a bit too small. Let's say 10. So it has like 10 stuff, and none of this is like initialized. So I'm just gonna run this. So if I just try to print x, it will be like none of this is initialized. Here's some weird stuff. So it's all 0 0 0. Okay, now let's say we actually put some stuff in x. So we'll put 1 till 10. That should be like, okay, it's just a range basically, right? So you don't have for loop, so I'll just do a while loop. So I equal to 0. So first let, because you're declaring a variable, that I equal to 0. And then, so yeah, by the way, this is like all multi-line. You can do whatever, like, so okay, it even gives you the thing. So it's while. So while I don't know, let's say I less than 10, you'll do something. What will I do? I'll, oh, by the way, you can do it like this. You'll yeah, okay, that's the problem, that it still does stuff on tab. I have to put a space inside of its prompts as well, but okay, whatever. So while I less than 10, one is like you have to increment it, because obviously that's a while loop, so that's how it works. And then you also have to do, so x sub, I don't know, I, that's equal to I, right? So 0 till 9, let's say. Yeah, this should be okay. So now I'll just execute this, works. And now if I try to print x, it's this thing. Now let's say, I don't know, y is some sine of x or something. Okay, sine of x is a bit problematic for this particular stream of numbers. I should have used some line space or whatever, but okay, I don't even have a line space function. I can put that, I mean, now you can put system calls to extend it. So I can put all of NumPy into this, but like, what's the point? It's just to showcase my language, not to showcase how it's done. But yeah, so I'm just going to use some very simple polynomial function. So I don't know, let's say something which is based around 3, I don't know, so it's like x square minus 6x plus 9 or something, x minus 3 square basically. So I'll just like x times of x minus, I don't know, 6 times of x plus 9, and you obviously have to do let, because you're declaring a variable right now. So I'll just do that, and I'll print what this thing is, just for your sake. And now the time comes to plot. So I'll be like plot x comma y, right? So this is actually not going to use a run or any kind of thing. It's just going to run normally. So I'll just be like, yeah, and it plots it. Yeah, so this is using a library called termplot_lib, and none of this is there in the compiler. All of this is there in the interpreter. So okay, that's enough introduction to what this language can do or should be. Okay, let's actually put a bit more stuff. Let's say, I don't know, we'll say x is some input, or let's say integer input, right? Input on enter some number, enter a number, right? And I don't know, we'll return x square. So we'll be like print I don't know, just x times of x. Fine, that's okay. Yeah, this should be okay. So I'll do like control J, enter a number, I don't know, let's say 10, 100. Yeah, whatever. It's very normal stuff. You also have like read, write, import. Import basically like takes in a file and then runs the code without actually initializing the whole thing, so it basically adds to whatever you were doing, so it like works just as you would have in Python. Now these things are not there in the compiler yet, right, because file management isn't there in the compiler yet. It's based on MIPS, and I don't know how to do that in MIPS yet is the keyword. Okay, but I do have input in like MIPS. But yeah, so to proceed further, I have to open a code editor, because like I really have to, you know, show you how the code looks. Okay, so I'll just exit. Interesting. I'll just exit. Okay, it exited, whatever. Now I'll be like, code this, and this is going to run with a lot of memory consumption, so I have to do it fast. But yeah, it's not going to take too much of time. Okay, so we are starting. So I don't know, I'm going to take some very simple thing. Let's take threesome, right? So threesome is an algorithm like this, and then this should run, or let's take subset sum. So yeah, this is fine. So subset sum is an algorithm which, like, given a subset, so given like a set of numbers, it finds if there's a subset which has the sum equal to some target. This is an NP hard problem. Do not dare to solve this, but yeah, I mean, we're going to do it anyway. So this is going to be the usual hard, you know, like brute force way of just finding the permutations. Yeah, so first what you have to do is, obviously you have to do compilation and all of that for the files, but I'll skip all these steps, and I'll just say, okay, first I am going to show you all the things which this shell command, shell script will do. Yeah, so it does all of this. It first does a bunch of like compilation stuff, then it like assembles it, and then it you know, executes the thing on a virtual machine. Okay, so I'll clear it again, and now I'll just run this. So chain.sh on this thing, so subset sum. This is in some folder, I think. Alright, so once I run this, it's going to take a bit of time. Now it's running. So program loaded. There are 1153 instructions. It's starting the execution. Since I'm okay, it actually fine. It did it anyway. This ran pretty quick, like as you just saw. And so the total instructions executed are these many. And this is like, so when I say total instructions executed, I should really like say total number of cycles, disregarding on all the pipelining faults that you might have. So all the delays that you would have to introduce, I'm not regarding any of that. So this will actually be slightly more than this, but it's still a good baseline. Like this is giving you an order, right? So you would have similar to this or twice of this number of instructions executed, right? So the cycles per instruction in a normal pipeline setup, it's not one necessarily, it's more than one, but it's also not too big, right? So this will be at max 3 times more than this. I think so. I don't really know how it usually goes, but I hope so that on Nintendo that's how it works, because the time for a clock cycle is what I have got from Nintendo, right? The Nintendo machine which uses MIPS architecture, and so it has. So I'm just going to like show you some pretty basic stuff. So so like this is number of instructions that you have. So this is our instruction count. Our so every clock cycle takes like 10.5 to the power of, so 10 times 10 power negative 9, so like nano seconds. So this is in seconds, right? And if I say the execution time, right, then it should just be the instruction count times TC, because CPI is 1, or we are assuming at least that it is 1 or something similar to 1, and so it would just run in 0.59 seconds, right? Now try running this same thing on a, like, I don't know, Python or something like that, and you would see it would be comparable to this. If not like worse, it would at least be comparable to this. You would have, I don't know, 0.2 or 0.1 or something like that, right? Okay. So like code this same thing in Python and then run that. I've actually done that for one of these samples. So like a Fibonacci number, very simple recursion, like brute force algorithm, and it runs almost similar when you like compute it on actual hardware versus when you compute it on Python. It actually runs kind of slightly faster because it's like we are not thinking of all the OS stuff that's happening, like all the you have to do a bunch of like context switching and all. None of that. We're not thinking of any of that, right? Okay, so this is cool, but what happened exactly? Like, what did this thing do? So first thing that it did was compile it. So to compile, you just do like com.py and then the subset something, right? So subset.algl. So you just input the file name for the .algl file, which is like this sort of thing. Oh, and it's syntax highlighted because of the Alsin VS Code extension. You already know about that, I think, from my past videos. So you first compile it, and then this is going to give you a .s file, right? So it got compiled, and then so it gave me this thing. Okay, so it has a .s file that it gave me, and it has a bunch of things. It has like the system calls, it has the main code for this, it has a bunch of load stores, etc., some error handling, type checking, dynamic type checking, by the way. So this is actually more problematic. It has all of that in MIPS. Just imagine how much of pain I had to go through to do all of that. But yes, this has fully functioning code. I've tested it a bunch of times with a bunch of programs, and I still keep finding errors because in the end this is like a big project. But this works. Trust me, this works. Okay, next what you do is you assemble it. So you'll be like, okay, don't laugh on the file names, but I couldn't think of anything better. So it's ass.py, that's what I've named it, this script, and then you'll just have the .s file. So .s and then this will give you an output basically, and also it will create hex codes for you. So that will be a .hex file. So if I do this, it does all of this. I'm just going to slightly increase the size so that it's better. Yeah, so it formats it with ANSI colors and all that, the usual, just so that you can understand it, just so that human can understand it. But what we really care about is none of this, because this is already hard to debug with so many instructions. This is like insane. If you try to debug it, you probably have to have some better thing to do, like I don't know how this is going to work in practice, although you have everything that you would potentially need to debug, but I don't know how this works in practice. I'll have to figure that out. Okay, so that's there. Cool. And next what you do, you have a hex file now. So I'll just show you the hex file. So this is currently just a text file, although it should technically be like in a real hex code, so that would be much smaller and also much easier to fit in the memory, but it doesn't really matter because it's in any case a small enough file. So it's just like 1153 instructions, not a big deal at all. That's very easy to fit in memory, and usually programs are very small, so you can fit it easily. Now you just execute it. So you're like exe. So exe was compiled when we ran chain.sh anyway, so you do .exe and then the hex file. So this is dsa subset sum whatever .hex, and then this will execute this thing. It has a bunch of options. One you can do a debugging option or a profiling option or whatever, but for now I'm just going to run it plain without any extra stuff. So we're starting execution, and it completed its execution. It printed whatever it had to print. It's found at permutation something, I don't care. Total instructions executed is still the same because it's deterministic, whatever. Next, I'm going to show you how the profile option works. So, and I'm going to show you how the debug option works, but this is going to be hectic. But yeah, so this one is easy to show. Okay, it's going to take some time. Right, so it gives me a whole summary of what instructions ran. So COP2, that's like the quantum coprocessor. Coprocessor 1 is just floating point instructions, and since there's nothing about floats going on over here, it's simple subset sum on integers. You have 0 floating point instructions. Then you have R type, J type, which you have 27%, 70%. Most of it is just I type. That's because there's a lot of add immediate, load immediate stuff going on. And then there's J types, which is very less, because I mean that's to be like that's pretty obvious it's going to be less, because J type instructions involve, by the way, I type I think also has branches or something. Yeah, I think so. J type only has jump and lick and jump. So branches are there somewhere. I think it's either in R type or I think it's yeah, it has an immediate. It has it's an I type instruction. So in I type instruction you also have branches. That's another reason why you have 70%. So conditional branching, that's like very important. So that was executing like a lot of times. Anyway, you also have add immediate, you have other stuff, and then you have R type, simple R type instructions, 27%. Combined, this would be the major workload. It's like 97%, 97.7% in fact is just R and I type. And then there's some jump instructions. Those are mainly for recursion, like function calls, those kind of things, and for while loops. That's it. That's all you would use J type instructions for. Simple jumps and jump and links, right? But JR is like a R type of whatever. Let's not talk about that stuff right now. But yeah, so now I'll do this with a debug mode, and this is a lot more hectic to explain. So I'm going to redirect it to some file. So I'll be like DSA subset sum dot debug. Alright, and then it's going to do the thing. Let's wait for a time. Come on, don't fade on me, not yet at least. Okay, let's just keep waiting. You know, this is a bad idea, considering it has to print a lot of stuff. So I don't know how long this is going to take. Like for every instruction, it's going to print stuff. This is insane. I shouldn't be doing this. I just realized that this is actually a very bad program to debug in the first place, because there's a massive workload. Okay, let's take some. Let's not do this actually. Let's take some smaller program. Okay, there's already a partial debug file. Yeah, it's very large. I get it. I'm going to delete it. That's I should have thought about this beforehand. So okay, let's take something smaller. Let's take one of these samples, right? So I don't know, I'm going to take something which did have a debug. Sample 10, I do not want to run its Fibonacci recursion. That would be too much. What's sample 11? This is bad because you do not have dictionaries yet. 14. This is simple. This is very simple. I can run this one. So I'll just be like chain.sh and then samples and sample 14.txt. Yes, A1 takes like txt files. It's not a big deal. And let's just run this. And there you go. It did whatever it had to did. Now you have a hex file, you have a .s file, etc. Now debug. So it'll be like exe samples sample 14, and we're going to use the .hex code stuff, and this is going to be in debug mode, and we'll redirect this whole thing to the same folder because I do not want to create a mess. So sample 14 dot I don't know, debug, and this should, yeah, this happened pretty easily. Okay, so now you have sample 14.debug, which looks like this. I'll just close this for a while. Okay, so you have, well, your state basically, like your general purpose registers. You do not have the floating point registers there because, well, just my choice, because I don't want to show it. You have some floating point registers, all right, very few in fact, but yeah. So I guess there's oh, you really don't have it, it seems. I think I didn't put it anyway, so you don't have that. You have the HI and LO registers. I don't even know how to call it. Is it registers or? I think it's registers because they are also 32. Okay. I mean, okay, it would be registered anyway. Like digital systems, why it would be registered, but like, what does it matter anyway? There's nothing like a half register. Okay, and then you have the amplitude for the quantum state, and the state vector, whatever, stuff like that. And then there's the normalization check, which it's printing for some reason. I think I should probably disable this, but whatever. So you have these instructions, and the address for these instructions is the same as what was there in the assembly output. So if you had the assembly output stored, you would just compare and you would know which instruction is going to be executed next, right? Also, these program counters are actually like not for the instruction but for the next instruction, because that's how it actually goes. So for this instruction, the output is this, and then the program counter is pointing to the next instruction. So this is printed after the instruction is done, basically, right? And just before the next instruction is going to be executed. So you do all of that. Right now it's like very less number of instructions, but yeah. So this is just a debug stuff. So this is useful when you really want to debug, like when you want to figure out what's going wrong. This isn't useful when you want to debug in a sane manner. So I have to figure out some better way to do this, but right now this works. In my painful way of debugging, I am somehow able to do all of this. Also, there's a disassembler which currently is broken, but when it was working, the disassembler would reconstruct hex codes to this. So 21.hex, it looks like this. That's what this sample 21.hex looks, and then it reconstructed it to this, which can run on SPIM. So yeah, my whole like code base is based around it running on SPIM. So I have two like shell scripts. So I have chain.sh, and I also have this run.sh, which I'll show you actually, which straight up runs stuff on SPIM, right? Not on the virtual machine. And I do not like this because SPIM is slow, but yeah, this was what was being used to actually build all of this. Like in the testing procedure, this is what was being used. And then you have this thing, it's a simple shell script for like testing. It doesn't really matter. Yeah, so all of this is cool. I guess that's it. This is it. So before I try to do the whole like assembler, disassembler, executor weird like toolchain thing, I was actually doing everything using the MIPS code itself, which turned out to be very slow. So I have like a virtual machine which is in C++ built around that idea, and this is actually really large. I shouldn't open this, but yeah, this was very slow, and that's why I switched. So I created like my whole like instruction format. So I'll just open a like I don't know, preview to site. Yeah, this is probably the better thing to preview enhanced. Right, so I had to do this sort of stuff, like, you know, for every instruction I had to figure out how do I like encode it, decode it, etc. And then so once it's like in hex codes, your C execution thing, right, your virtual machine, it runs pretty smooth. It runs extremely fast on that. Even though it's just a virtual machine, it runs fast on that. And just imagine how it would be on a real hardware where you have decoders and some actual fixed program logic going on, like which doesn't really use the RAM of this computer, this virtual machine thing, and it's just running straight up on hardware. That would be very cool. That would be like fast, isn't that right? But yeah, so I had to do all of this stuff. I even had to like figure out what do pseudo instructions map to, and this caused me a bunch of pain because I was using load image at places I shouldn't be using, and then SPIM thinks that load image is just like one instruction, and yeah, that was a pain, a real big pain, and I had to change a lot of code because of that. But yeah, it worked out. In the end, it just worked out. So this is it. This is my compilers project. I think it's pretty cool. We also did a bunch of assignments. One was like building a fourth like language. That was very fun. I had a whole discussion about like the like what this can and cannot do. Like, is it going to be a universal Turing, or what is it called, universal Turing machine or something like that? Can it actually simulate other Turing machines and stuff like that? Because the way that we were building in the first few labs, it was really just a push on automata sort of thing. So after we added some few extra things, like I don't know, variables and symbols and functions, it became like full on a Turing machine. But till that point, it was just a push on automata, and yeah, so we had fun doing that. Okay, now battery is running low, so I'll just stop this. But yeah, this is it. I'll see you guys in the next video.